Welcome to the deep dive. Today we're heading out to the really extreme parts of the cosmos. We're talking neutron stars and pulsars.
Absolutely. These aren't your average stars.
No, definitely not. They're what's left after a really massive star explodes, right? A supernova.
Exactly. The collapsed core.
Hmm.
And the density is just staggering. Imagine squeezing more mass than our entire sun into something the size of a city.
That's almost impossible to picture, like taking an atomic nucleus and scaling it up.
That's a pretty good analogy, actually. And from these super dense objects, we get pulsars.
Okay, so pulsars are a type of neutron star.
Yep. They're neutron stars that spin incredibly fast, and they have these unbelievably strong magnetic fields.
And they pulse? Is that why we call them pulsars?
Precisely. They shoot out beams of radio waves from their magnetic poles.
Huh.
But here's the thing. The magnetic poles usually aren't lined up with the spin axis.
Ah, okay. So as it spins.
The beams sweep around like a lighthouse.
Mm.
And if one of those beams happens to sweep across our line of sight here on Earth,
We see a pulse, like a cosmic lighthouse or maybe a sprinkler.
cosmic sprinkler, I like that. And yeah, you only get hit by the beam periodically as it rotates.
And I hear there are different kinds, like normal ones and really, really fast ones.
That's right. You've got your normal pulsars, spinning maybe once a second, give or take.
Hmm.
But then you have millisecond pulsars.
Millisecond. So they spin hundreds of times a second.
Some do, yeah. These are generally older neutron stars. They've been spun up
Spun up. How?
by pulling in material from a companion star in a binary system. It's like, well, it's accretion. As the matter falls onto the neutron star, it brings angular momentum with it.
So it's like pushing a roundabout. It spins faster and faster.
Exactly. A cosmic roundabout powered by a neighbor. And often, even after they get spun up, they still have that partner orbiting them.
What kind of partner? Another neutron star.
Sometimes, yes. Or often a white dwarf star, the remnant of a smaller star.
The numbers are just wild. You said about 2,600 known pulsars.
Around that, yeah. But that's almost certainly just, the tip of the iceberg. There are likely way more we haven't found yet.
And the millisecond ones?
We know of over 80 just in the main disk of our galaxy, the Milky Way.
Mm.
Maybe under 30 or so packed into those dense star clusters, globular clusters.
And the speeds. Didn't you mention one spins over 700 times a second?
Yeah, PSRJ 17482446 adder. It clocks in at 716 hertz. That's a rotation every 1.4 milliseconds. Just mind-blowing speed.
And the slowest. Is there a slow poke pulsar?
There is. PSRJ 21443933 takes a whole 8.5 seconds for one rotation. Almost leisurely in comparison.
So these extreme objects, they must be amazing laboratories for physics.
Oh, absolutely invaluable.
Hmm.
We can study states of matter, nuclear physics, under conditions we just can't replicate on Earth. Understand how their winds transport energy.
And knowing how far away they are must be pretty crucial for all that.
Essential. You need the distance to figure out their true brightness, their energy output. Also, tracking their motion tells us about supernovae, how they got kicked maybe, and how binary systems evolve.
Okay, so measuring distance is key. But how do you measure the distance to something so small and, well, often faint and far away? Sounds tricky.
It definitely is a challenge. The main method for most radio pulsars uses something called the dispersion measure.
Dispersion measure? What's that?
Okay, so radio waves travel through space, right? And space isn't perfectly empty. There are free electrons floating around in the interstellar medium.
Yeah.
When the pulsar's radio waves travel through these electrons, the waves get dispersed. Higher frequencies travel slightly faster than lower frequencies.
Ah, like a light through a prism, but with radio waves and electrons?
Sort of, yeah. It causes a tiny delay in the arrival time of the lower frequency waves compared to the higher frequency ones.
Mm-hmm.
We can measure that delay very precisely.
Okay.
And that delay tells us the total number of electrons along the line of sight between us and the pulsar.
But how does that give you a distance? Don't you need to know how densely packed the electrons are?
Exactly, that's the catch. To convert the electron, count the dispersion measure into a distance, you need a model of how electrons are distributed throughout the Milky Way.
And those models, are they perfect?
They're getting better, but no, they're not perfect. There are variations in structures in the interstellar medium we don't fully know. So dispersion measure distances are, well, estimates. Good estimates sometimes, but with uncertainties.
Like trying to gauge distance by counting raindrops on a windshield, maybe? You get a sense, but it's not exact.
That's a nice way to put it. So we really want more direct methods if possible.
Are there other ways? More direct ways?
Thankfully, yes. Sometimes a pulsar is in a star cluster. And if we know the cluster's distance from studying its other stars, we know the pulsar's distance too.
Okay, that makes sense. Association.
Right. Or if the pulsar has a visible companion star, like those white dwarfs we mentioned, or maybe even a more normal star, we can try to measure the distance to the companion, maybe using spectroscopy on the companion star to figure out its true brightness, that's spectroscopic parallax. Compare true brightness to apparent brightness. Get the distance.
Got it. Use the partner star.
Exactly. And for some nearby pulsars, we can actually measure the timing parallax.
Timing parallax.
Yeah, as Earth orbits the sun, our viewpoint shifts slightly. This causes incredibly tiny but measurable annual variations in when the pulses arrive. You need microsecond accuracy, but it gives a geometric distance.
Wow. Microseconds.
And then there's the gold standard for radio sources, VLBI, Very Long Baseline Interferometry.
Right, linking radio telescopes across Earth.
Yep. Creates a virtual telescope the size of the Earth, giving incredible angular resolution, enough to directly measure the tiny shift in a pulsar's position against background objects as Earth orbits the classic parallax measurement, direct geometric distance.
Okay, so several methods, but some are tricky or only work for specific cases. Now, where does Gaia fit in? It maps stars optically, right?
That's the key question. Gaia is mapping over 1 billion stars with unbelievable precision, measuring their positions, motions, and parallaxes.
But you said most pulsars are too faint optically. I think only the Crab pulsar is bright enough.
That's generally true. But Gaia's genius here is observing the companions.
Ah, the partners in those binary systems again.
Exactly. While the pulsar itself might be invisible to Gaia, its white dwarf companion, or maybe a non-degenerate star in one of those Black Widow or Redback systems.
Those are the ones where the pulsar is kind of eating its companion, right?
Sort of, yes, stripping material off. Those companions can be bright enough for Gaia to see and measure extremely accurately.
So Gaia measures the partner's position and movement really, really well.
Incredibly well. Gaia's data release, too, back a few years ago was a game changer. It included fantastic data for the companions of known pulsars.
So it's like studying the leash to understand the invisible dog pulling on it.
Ah, that's one way to look at it. You study the visible partner to learn about the system, including the distance to the unseen pulsar.
And people have used this data already.
Oh, yes. There was a key study, Jennings and colleagues, in 2018. They took a big catalog of pulsars, not the ones in globular clusters, and cross-matched them with Gaia DR2.
Did they find many matches? Companion stars in the Gaia data?
They found 22 systems where a known binary pulsar's companion had a Gaia counterpart. And crucially, for 12 of those, Gaia gave a statistically significant parallax measurement for the companion.
12 direct distance measurements. That's a big deal.
It really is. It gives us independent geometric distances to benchmark against those dispersion measure estimates and other methods. More reliable cosmic rulers.
And were these just any old pulsars, or were some of them particularly interesting?
Some were very important systems, ones used to test Einstein's theory of gravity, for instance.
Like really precise tests of general relativity.
Exactly. Systems like PSR J0348 plus 0432. Others are crucial for understanding how accretion works, like PSR J1023 plus 0038, which switches between states. And even systems like PSR B125963 that help us study particle acceleration in extreme environments.
So Gaia is helping us test fundamental physics just by measuring these companion stars accurately.
That's the power of precision astrometry.
So what was the bottom line from that Jennings study? Did the Gaia distances generally match what we thought before?
Broadly speaking, yes. There was reasonable agreement between the pre-Gaia distance and proper motion estimates and the new Gaia results.
Okay, so no huge revolution there.
Well, not a complete upheaval, but Gaia provided a definite improvement. A small but statistically significant refinement to the overall pulsar distance scale.
And that helps with other areas.
Definitely, especially for millisecond pulsars. More accurate distances improve their usefulness for pulsar timing arrays.
Ah, the project's trying to detect gravitational waves using pulsars, the super low-frequency ones.
Exactly, nanohertz gravitational waves. Better distances mean the timing models are more accurate, making the array more sensitive to those faint ripples in spacetime.
But it wasn't all agreement, was it? Weren't there some discrepancies too?
Yes, and this is really interesting. The study suggested that those common dispersion measure models like NE2001 and YMW16 might systematically underestimate the distances compared to Gaia's parallax measurements.
So our maps of electrons in the galaxy might need tweaking?
It certainly points that way. Gaia is providing a crucial check on those models, and it gets even more interesting when you look at individual systems.
Like specific cases where Gaia threw up a puzzle.
Right. Take J0437471 Phi. It's one of the closest, brightest millisecond pulsars, really well studied. Gaia's distance measurement for its white dwarf companion is quite a bit smaller than estimates based on orbital period changes.
Smaller. Why would that be?
The suggestion is there might be some subtle, unmodeled motion within the binary system itself affecting the older estimates. Gaia's direct parallax cuts through that.
So even for the famous ones, Gaia finds new things. Any others?
Yeah, for J474402, the Gaia distance really supports the idea that its companion star is puffed up and filling its Roche lobe, its gravitational boundary. It makes the older dispersion measure distance look less likely. Then there's J1816 plus 4510. Gaia's measurement of how fast it's moving across the sky, its proper motion, disagrees quite significantly with what pulsar timing suggested. So we need to figure out why those differ.
A mystery there.
For J2032 plus Fortness 127, it's in a really wide, long-period binary. It takes about 46 years to orbit. The thinking is that maybe this wide orbit made it harder for Gaia to pin down the companion's motion perfectly over the DR2 observation period.
That makes sense. Need to watch it for longer.
Possibly. And one more, J2215 plus 505135. There was an older, proper motion estimate that Gaia showed was just way off, probably erroneous. So Gaia is also cleaning up some past errors.
Like a celestial fact checker. Okay, let's shift gears slightly. We know most massive stars, the kind that become neutron stars, are born in binaries or multiples.
That's right, yeah. The majority start with partners.
But you often hear that most pulsars are found alone, isolated. Why the difference?
The leading theory is the supernova kick.
Ah, the explosion itself gives the new neutron star a massive shove.
Exactly. When the core collapses and the outer layers rebound, the explosion isn't perfectly symmetrical. This asymmetry can impart a huge velocity, a kick, to the neutron star, hundreds of kilometers per second sometimes.
And that kick can break up the binary.
Often, yes. If the kick is strong enough and in the right direction, it can exceed the gravitational binding energy of the system, and the two stars fly apart. The neutron star goes one way, the companion, if it survives, goes another.
So that explains why many seem isolated. But maybe some do have companions we just haven't found yet.
That's also possible. The companion could be very faint, or maybe we just haven't timed the pulsar long enough to detect the wobble caused by an unseen partner. Gaia's precision helps here too, searching for faint nearby stars that might be moving with the pulsar.
And didn't another study use Gaia specifically to look at this binary fraction, Antonius in 2021?
Yes, precisely. Antonius used Gaia DR2's super accurate positions to search for companions near a large sample over 1,500 pulsars with really well-known locations.
What did they find? Lots of hidden partners.
They confirmed several known companions, which is a good sanity check. And they did find several new potential companions, particularly around young pulsars.
But overall, did it change the picture much? Still mostly solo?
The overall picture still points to a low observed binary fraction. The study put a tighter constraint on it, suggesting that fewer than about 5% of young pulsars have companions detectable by Gaia or known through timing.
Less than 5%.
Yeah, though they acknowledge there could still be fainter binaries below Gaia's limits. But this 5% figure is important.
Why?
It helps constrain how often neutron stars merge in our galaxy. Those mergers are sources of gravitational waves and heavy elements. So knowing the binary fraction helps estimate the merger rate.
Ah, connecting pulsars to Lega Virgo detections and gold production?
In a way, yes. And just like the Jennings study, this work also flags some individual systems where the Gaia data suggests we need to revise our models of the binary orbits. Gaia keeps refining things. It really does. Okay, one last area. Pulsar velocities. We mentioned the kicks. How accurately can we measure how fast these things are zooming around?
Getting accurate velocities is super important for understanding the kick physics and how binaries evolve post-supernova. This brings us to work by Yang and colleagues, also in 2021.
What did they do? More Gaia data.
Yes, they use Gaia DR2 data for young pulsars where we have good distances, but they also looked at all the other Gaia stars nearby these pulsars.
Why look at the nearby stars?
To get a really good handle on the local kinematics, they measured the velocity of the local standard of rest, basically, the average motion of stars in that specific patch of the galaxy, and also how spread out the velocities are, the local velocity dispersion.
So they mapped the local traffic flow around the pulsars.
That's a good way to think about it. They found their calculated local standard of rest was pretty close to standard galactic rotation models, but there were bigger differences for pulsars located far above or below the Milky Way's disk.
Suggesting the dynamics are different out there. Yeah, maybe less settled, more complex motions further from the plane. But the really key finding related to the pulsars and their kicks.
What was that?
They found that for the slower moving pulsars in their sample, the typical velocity spread of the nearby stars was often similar in size to the pulsar's own velocity across the sky.
Wait, the background stars are moving around as much as the pulsar is? What does that mean?
It means you can't just assume the pulsar's velocity is all due to the supernova kick. The original motion of the progenitor star, the star before it exploded, must have played a significant role too.
Ah, so the kick adds to whatever velocity the star already had.
Exactly. You have to consider the progenitor's velocity when trying to figure out the true size and direction of the natal kick and how the system evolved. It adds another layer to the puzzle.
So even just using Gaia's initial big data releases, focusing mostly on positions and motions, often of the companions, we've learned a huge amount.
Tremendous amount. Improved distances, better understanding of binaries, checks on our models of the galaxy, insights into supernova kicks,
Oh.
all from Gaia's precise view.
It really underscores the power of just measuring where things are and how they're moving, doesn't it?
Absolutely. And remember, this is mostly based on data release 2. Future Gaia releases will bring even better precision, more objects, and likely many more discoveries about these incredible remnants.
Okay, let's wrap up this deep dive into neutron stars and pulsars. We've really seen how Gaia, even by looking at the partners of these extreme objects, is sharpening our view.
Yeah, better distances, a clearer picture of binaries, new constraints on velocities, checks on our galactic models. It's quite a contribution already.
It really highlights how these faint companions hold keys to understanding the pulsars themselves, these places, with physics unlike anything on Earth. Densities, magnetic fields, just wow.
And their role as cosmic clocks, potential gravitational wave sources. It's a field full of extremes and deep questions.
It definitely leaves you wondering, with future data, what other astonishing secrets are these neutron stars waiting to reveal? Thanks for joining us on this Doom Dive.